So in our last lesson, we looked at the structure of the atom and we focused on the electron. Okay, we're going to continue on and look at the protons and the neutrons in this lecture. Now, what did we end with last time? We ended with this question, okay? Because in that last lecture we saw that electrons existed, electrons were negatively charged. We learned they were very tiny. We know that the electrons are housed within the atom, but the atom is not negative. It is a neutral entity. So which one of those did you come up with, which had to be the next logical thing to state about an atom? And do you remember? Yes, that there was something positive inside of there. Okay, so we know there has to be something positive. So let's look at the experimentation that led to this. Okay, the first thing that they looked at was this idea, okay, I know the atom is positive, I know there exist these little negative things in there, and this led to what we call the plum pudding model. I love that. Nobody's eating plum pudding anymore. It's a rare thing for somebody to eat plum pudding, but plum pudding is like oh, let's just say vanilla pudding with raisins in it, or a chocolate chip cookie with chocolate chips in it. What they thought was that the atom would be a positive sphere, okay? So we had this positive sphere with these electrons kind of embedded in the sphere like plums in a pudding, okay? That's the plum pudding model. And so that's kind of what Thomson, with his first discovery of these electrons, kind of thought. The atom itself was kind of a positive diffuse sphere with these electrons plopped inside of it. Okay, now, nobody comes to chemistry class thinking that's what an atom looks like. Many of you, if you even learned about plum pudding models, learned about it and went on with life and didn't remember that piece of information. But there was experimentation that got us to where we understand atoms today, which is with a positive nucleus. So let's see how that came about. Okay, before we can do that, we have to understand a little bit about radioactivity. So this is kind of a side note to give us a foundation of what we need to know in order to do the experiment that we'll examine next. So what is a radioactivity? It's a spontaneous emission of particles and or radiation from a substance of some sort. Okay, so it just spontaneously gives off particles. Now, they didn't know a whole lot about these particles, but they did understand about radioactivity and that something was coming out of this substance that they could measure. There are alpha rays. Now, what alpha rays are positively charged particles, and we actually know now today that they're like little helium nuclei that are being emitted out of a larger nucleus. That's what an alpha ray or an alpha particle is. So they knew they were positively charged. They carried a little bit of mass with them. Then there were beta particles, or beta rays, and beta particles are basically just electrons that are being emitted out of the nucleus, which we know about today. They didn't know about it back then, but they're these tiny negatively charged particles. There are also gamma rays, and gamma rays are just high energy radiation. They contain no mass, no charge at all, but are high energy. And so if you have a substance that is radioactive, it will spontaneously emit typically one of these three particles: an alpha ray, a beta ray, or a gamma ray. So Rutherford took his knowledge of radioactivity and he set up an experiment. So let's look at his gold foil experiment. Before we do, let's kind of give you a preview of what he discovered. What he discovered was that Thomson's model was not accurate. Remember the plum pudding model? You got your plum pudding and you got the electrons kind of stuck in there like plums in the pudding. His experiment, we're going to see, completely disproved that model for the atom. What he showed with his experiment, we're going to see, is that when you consider the atom, most of it is empty space. It's a vast emptiness, but it has a very tiny, very dense central core. Okay? He called this core the nucleus, and most of you are going to be familiar with that term. So how did this experiment do that? Oh, and that's where all the positives being held. There in that nucleus, all the positive charge is made up of particles, and these particles are what we call protons. So here's the experiment. Inside of here is the radioactive source. This radioactive source is actually alpha particles that are coming out of this source and moving through. This is a detector screen. Now what happens with this detector screen is it lights up Okay, it lights up when it gets, that's me doing light, okay, it gets struck by these particles. And he had a little opening here that allowed the particles to come in. They struck the gold foil and most of them hit right back here, right on the other side of this. I'm not sure that's the right one. It might have been this one. It doesn't matter. It struck right through the gold foil. Most of them did that. But not all of them did. Some of them got deflected a little bit, and so they shot off to the side. Some of them got deflected a little bit more. But what was most remarkable for him is some of them hit the surface and bounced back. Okay, they hit that gold foil and didn't go through. Now, they expected all of them to go through. Have no deflection, just pass right on through. If it was a diffuse body that it was going through, and these alpha particles, okay, these alpha particles that are going through are much bigger than electrons, and the rest of the atom is just kind of this diffuse positiveness, they expected them to all pass right on through. Didn't find that to happen. Okay, so this is what Rutherford said about what he discovered. He's like, this was incredible. It's as if you took a 15-inch shell and fired at a piece of tissue paper and it came back and hit you. You would not expect that to happen. That would be a very unusual thing. And yet that alpha particle absolutely did a similar thing. It hit this little piece of gold foil and it bounced right back. Now, how in the world did that lead to what I said it led to on the previous slide? How did this lead to the fact that most of the atom is empty space, that we have a very dense central core that contains the protons? Well, let's think about it. On the left is the plum pudding model, okay? If we had this diffuse, try that again. If we had this diffuse core, okay, then most of them would pass right on through, no problem, because those alpha particles are much bigger than the electrons and they would just pass right on through. That didn't happen. Some of them bounced back. So the nuclear model helps us understand that. Why would some of them bounce back? Well, most of them go through because they're just going through this empty space and they're striking that detector over here on this side and lighting up. But every once in a while, one's going to come and it's going to get deflected a little bit. So here's one that's getting deflected a little bit. Why a little bit? Well, that alpha particle is positively charged. And what do we know about like charges? They repel. So if it gets close to this nucleus, which itself would have to be positively charged, it would be deflected away from it. Every once in a while, and this was a rarity, every once in a while an alpha particle would come in and actually make contact with that tiny little nucleus. It doesn't happen very often because the nucleus is so teeny compared to the rest of the space. And if it were to strike it, it would bounce right back off. And so this gave us the idea that that nucleus was very tiny because most of them passed through, was positively charged because it deflected some of those alpha particles who themselves were positively charged. Okay, so this is the mass of a proton, and at first glance, well, we see that that's very tiny, but it's a lot bigger than the electron, okay? 1,840 times more massive than the electron. Don't memorize that number, but it is much bigger. So if I had a dump truck and I pulled off one little piece of coal off the top of the dump truck is still very heavy. That piece of coal was not much. That's kind of the difference between the dump truck and the piece of coal. Okay? Now, what they discovered with these protons is that they were the same size charge, but opposite. Okay, so they're bigger, but they contain exactly the same charge as the electron, but they're positively charged instead of negatively charged. What they determined by the number that actually passed right on through the atom and didn't strike anything and the few that bounced back is that the nucleus is much tinier. Okay, 10 to the 13th times the volume of the atom. Now let's stop and think about that for just a minute. Let's imagine a marble. And this marble was the nucleus of the atom. Okay, so we're blowing up the nucleus so it's the size of the marble. And then we have to think about, well, okay, if that's true, how big is the rest of the atom? And so often, if we show this as the nucleus and put some positive charges in it, we might show the atom this big, all right? That is not a very good depiction of it. So we've got our marble. Now let's suspend this marble from the 50-yard line of a large football stadium. Let's consider our football stadium here at UK. If we suspend that marble above the 50-yard line, the rest of Commonwealth Stadium would be the atom. So I couldn't, if I drew my marble this size, the atom would not fit on this piece of paper. Okay, so let's get that in mind. The nucleus is tiny compared to the rest of the atom. The rest of the atom is basically empty space for those electrons to buzz around in. So we have our electrons. We learned about that in the previous lecture. We now have our protons. We understand that protons contribute a lot of mass to the atom. They contained in a tiny little nucleus, and they started examining these atoms. And they started by examining the simplest two elements, okay? The hydrogen atom and the helium atom. This is what they knew about them. They knew the hydrogen had 1 proton and the helium had 2 protons. So let's imagine the proton and the electrons for just a minute. So for our hydrogen, okay, it would have 1 proton. I'll represent that with a plus sign. It had 1 electron, and I'll represent that with the minus sign, and that's my hydrogen atom. Okay, and the electrons weigh way little compared to the proton, 2,000 times less. So basically a hydrogen atom is the mass of the proton. Then we have the helium. The helium, on the other hand, has 2 protons, okay, and also 2 electrons. So I'll let that represent the things that a helium atom is made of that they knew about at this point. And they knew that the helium with its 2 protons and those 2 tiny electrons, that most of the mass of the helium would be due to the protons. So what they would expect to have seen is that the hydrogen would be, and the helium mass ratio should be 1 to 2. Stop and ponder that for a minute. Why does the first statement lead us to believe that the second statement would be true? Okay, once you've grasped that, then they started doing the observation, and what they really observed was this. It wasn't a 1 to 2 ratio of mass. It was a 1 to 4 ratio to mass, that the helium weighed 4 times more than the hydrogen. Well, if you look at what I've written in red, this would never account for that effect. What I see written in red would say it's 2 to 1 or 1 to 2. And they found it was 1 to 4. So I want you to kind of stop and think, all right? What would I decide if this were true? What would be the logical conclusion if the ratio is 1 to 4 instead of 1 to 2? Once you've pondered that and thought about it a little bit and exercised those muscles of yours in that head, then resume and see if what you kind of came up with matches what they came up with way back when. All right, well, this is what they said. There must be something else in there besides protons and electrons. Because if the protons and the electrons were the only story, and electrons don't contribute enough mass, it's like saying I took off this hair off my head and now I weigh less, it doesn't add enough mass to make any difference, okay? If we know that the electrons aren't contributing, what is happening? Well, there has to be something else contributing mass. And that is absolutely what happened, okay? The next particle that they knew had to exist was something else not having any charge, because we've taken account of the things that are positively charged, we've taken into account the things that are negatively charged. They don't have any charge, but they are adding mass to this atom. And so they proposed that neutrons existed. And so the proposal that they existed came way before the actual discovery. The discovery was by Chadwick, and it took a while to discover them because it was very hard to get a handle on them without having a charge to use to detect them. But they eventually did, and they said, yes, they do exist. Okay? Now, these neutrons, they have no charge, as it says here, no charge. They are slightly, just ever so slightly, more massive than the proton. I mean, just a hair more massive than those of the protons. And so let's look at how this accounts for what we saw. Well, the hydrogen atom had 1 proton and, of course, 1 electron, but no neutrons. Okay? So the 1 proton is giving it mass. It doesn't have any neutrons. But the helium, it had the 2 protons and the 2 neutrons. So we have 4 pieces that are contributing mass. We have the electrons that are so light that aren't doing much. And so now we can say, aha, that explains why the relative mass would be 1 to 4. 1 proton and no neutrons versus 2 protons and 2 neutrons, knowing that the 2 protons and the 2 neutrons are about the same mass. That adds up to 4, and that gives us the mass of that helium being 4 relative to the mass of the hydrogen being 1. So now, what have we done? We've examined the atom. In the previous lecture, we saw the electrons, that they're negatively charged. Because the atom contained negatively charged things, we knew it had to have positively charged things. We saw the Rutherford-Goldfoyle experiment giving us an indication that all of that positive charge is within the nucleus. We have those protons carrying that positive charge in the nucleus. And then we also know that the nucleus contains as well the neutrons. So we're not going into the detailed experiments of how they discovered the neutrons, how they discovered that those two were also contained in the nucleus, but they are there to help hold that nucleus together, because those protons getting really, really close together are going to try to repel each other, and without those neutrons in there holding it together, the nucleus could never have more than 1 proton in it. So that is the discovery of the components and the parts of the atom.